Welcome back for some more about series, and in this particular video we are going to be looking at the Taylor series, which is a special type of power series, or at least it stems from power series. And so on top, the first major line, you could see a power series about A form that you became familiar with in the last video. Some of the derivation for getting your Taylor series is explained here, and so if you haven't read this, please read it at your leisure. But just to briefly describe the process of the derivation, notice that when f of x is evaluated at a, that all of the series terms disappear except for c0. So f of a is c0. If you take the first derivative and evaluate at a, then c1 will remain. If you take the second derivative and evaluate at a, then 2c2 will remain, and so forth. And the pattern that will come about is that the nth derivative evaluated at a will be equivalent to n factorial times c sub n, which means that if you solve for c sub n, you get the nth derivative at a divided by n factorial, and if you plug that in to your power series notation up above, you get this form right here. And so that is what we are going to make use of. What I highlighted in the next line is a special case of the Taylor series when a is the particular value of 0. That is called the Mclaren series. So let's take a look at the first example, which is asking for the Maclauren series of f of x equaling e to the x. Based on the general form that we had just seen, I know that we're going to need the derivatives of this f of x function, and so I'm going to just get a few of these just to start us off. And this is going to be f sub n evaluated at a, but remember a is 0 for the Maclauren series. And so f of x is e to the x, e to the 0 is 1. The first derivative is e to the x, and evaluated at 0 is 1. And the second derivative is also e to the x, evaluated at 0 is 1, and so forth. So this happens to be a pretty easy one in terms of the derivatives. And then what I do with those derivatives is I'm going to divide them by the n factorial. And so according to the series expansion, we have 1 is f of a plus the first derivative over 1 factorial times x minus 0 plus 1 over the second derivative factorial times x minus 0 squared plus 1 over the third derivative factorial, or 3 factorial, times x minus 0 cubed, which means that e to the x's Maclauren series expansion is 1 plus x plus 1/2 x squared plus 1/6 x cubed onwards. And that is the Maclauren series expansion for e to the x. For part 2, we want to get the Taylor series expansion for sine of x, but instead of going about a of 0, we're going about a of pi. And so here, I'm going to do this all in one shot. Sine of x is given by sine of pi plus, we've got cosine of pi divided by 1 factorial times x minus pi plus negative sine of pi over 2 factorial x minus pi squared plus negative cosine of pi over 3 factorial times x minus pi cubed. And you see the general pattern. And so the denominators of the coefficient parts are always n factorial. So there is a 0 factorial in the first term, but 0 factorial is 1. And then you have 1 factorial, 2 factorial, 3 factorial, and so forth. The numerators are the nth derivative of f evaluated at pi. So sine, derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, and so forth. And then you're just multiplying by x minus pi to some power. And what's left is to actually evaluate these. And so sine of pi is 0. So this term disappears, this one disappears, pretty much every other term is going to disappear. And cosine of pi is -1. And so where does that leave us? Well, that means we have -1 over 1 factorial, which is -1, x minus pi. Then we have -1, which is 1 over 3 factorial, 6, times x minus pi cubed. And even though I didn't go far enough, I'm going to throw in the next term, which is going to be a -1 over 5 factorial. So that's going to be 120. And that will be x minus pi to the 5th. So the series is alternating between plus and minus. And that is our Taylor series expansion about pi for sine of x. Now, you could do some neat things with Taylor series. For example, in the next problem, we want to determine the Taylor series expansion of cosine of x. And I know that the cosine of x is the derivative of sine of x, which means that since sine of x has the expansion that we just got in problem 2, I can just plug that expansion in and take its derivative. And so let me rewrite that expansion. We have -x minus pi plus 1/6 x minus pi cubed minus 1/120 x minus pi to the 5th, and so on. And when we take the derivative of this, we have -1 plus 1/2 x minus pi squared minus, that is going to be, let's see, 6 times 4, 1/24 x minus pi to the 4th. And that would be our Taylor series expansion. You could have viewed it a little differently and done the integral of negative sine, and that would have given you something similar. You would have lost the constant term, but you would have gotten the 1/2 x minus pi squared and the 1/24. And so you would get most of the other terms remaining. Derivatives are usually easier to get. Finally, part 4 wants the Taylor series expansion of x times cosine of x, which we have the expansion of cosine of x in part 3. So if I multiply that by x, I have x times -1 is negative x, plus x times 1/2 x minus pi squared is x over 2 times x minus pi squared, minus x over 24 x minus pi to the 4th, and so on. And that would be your expansion here. And so there are some tricks you just have to keep in mind that you may be looking for a derivative or an integral, but something along those lines where you already have part of the series and you're just multiplying by a term. So keep these tricks in mind as you progress through the work. Good luck.